Hi everyone, I'm FD0. Today I want to tell you something about programming Atmel microcontrollers. I had a problem, and that is I have 1 hour, and it's actually difficult to explain in 1 hour what I've worked on myself over 3 to 4 months. I will try. It may work, it may not. We'll see. I hope you all rate me. There's a nice feedback system in the schedule. Just click on it, rate it. It helps me, and it helps conference planning for next year, whether they want me again or at all, to rate speakers. So the other thing is, please turn off your cell phones. I did it too. It's hard for me too. We've got that covered. Otherwise, what else did I want to say, Dirk? Yes. Otherwise, exactly, if you have questions, please raise your hand and wait until you get a microphone, because otherwise we don't get the questions recorded and I have to repeat them. So just wait, and you will get a microphone, can ask the question, and then we'll continue. So the lecture is called AVR Atmel for Dummies. That means Dummies is not meant to be offensive. I don't think you're stupid, otherwise you wouldn't be here. But it's just that, especially with microcontrollers, the learning curve is incredibly steep. I mean, you have to, on one hand, you have to learn the software. So you have to learn how to program the thing. For one thing, if you haven't been doing this all along, you don't really know exactly what's going on. That's how it was for me, at least. My father has been doing this for 20 years. It wasn't so difficult for him, but I found it relatively difficult to even realize that I need a hardware circuit that works. And I need software that works, and I have to know the hardware. Those are 3 huge problems, and that makes the learning curve incredibly steep at the beginning. That's why there are several good sites on the net, like microcontroller.net. At the end, which isn't included in the slides yet, I'll add a reference list with URLs, with introductory tutorials, so that when you look at the slides again, you can also find the links. So let's just dive in. If I now, exactly, so the overview. I wanted to briefly introduce the Atmega 8, which is an 8-bit RISC CPU from Atmel. We'll continue by briefly mentioning it can't be extended any longer, unfortunately, how to program the thing, because somehow the program has to get from the computer through the compiler and then onto the microcontroller. Otherwise, we have the problem that there's no program on it. And the thing is quite boring if nothing happens. So there's on one hand the possibility to buy a commercial solution. It's just a cable that you plug into the computer. The other cable is attached to the hopefully functioning finished microcontroller circuit, and you program it. There are solutions ranging from 20 euros to 200 euros, depending on what you want. The alternative is simply a small homemade cable, which we'll see then. There's another alternative, simply to provide the Atmel for the first time with a small additional program, a bootloader, and then program it through that. It has several advantages, which we'll see then. The second part, which is actually the largest part, deals with the software within the Atmel itself. On one hand, there are different memory areas in the CPU, which we will briefly discuss because it's just one of those things with legs. You can't really see directly what exactly is inside it. Then we'll see what instructions look like, and we'll do quite a few examples of them. I don't know yet if the time will be sufficient. Maybe we'll do it again. Unfortunately, I brought a little Schnordlicht with me. I fear the room is too long for anyone to see anything except the first 2 rows. Therefore, we'll probably leave it out. We'll have to see. So let's get started. The Atmega 8. I thought about it. I built the Snort-Lite. There was an article about it in Datenschleuder, and I looked at it beforehand. What do I actually want? And I looked at what microcontrollers are available and which ones best meet my requirements. So on one hand, it was a requirement that it must be inexpensive. I can't spend 200 euros on a microcontroller. That doesn't work. It must be easy to program. I've never worked with microcontrollers before, so it must be learnable for me within a usable time frame. Otherwise, it doesn't help me. If I have to study for 2 years first, then it doesn't help me. It should have as many inputs and outputs as possible, because I want to do many interesting things with it. I don't just want to turn LEDs on and off. I also want to react to buttons. I might want to attach an infrared receiver. I want to attach a radio clock, whatever. And it must, that's the nice thing about the Atmega 8. It's a pretty simple CPU and can directly have LEDs attached to the outputs, for example. That works quite well. And you can simply, when you have the Atmel like that, attach an LED directly to one pin and play around with it, like turning it on and off, or dim brightness. And what was personally very important to me was that I wanted to be able to develop on a free operating system. I don't want to rely on Windows software, and that's the case with Atmel. There are quite good compilers. They also have their quirks, but they can, of course, be improved. And above all, there are free programming devices. So on the one hand, there's the hardware, as we just mentioned, and on the other hand, there's the software, which simply ensures that the program, as it exists as a file, somehow ends up on this little black thing with the pins. So a simple programming cable, let's start with that, because it somehow begins with trying to get your program onto the Atmel. This is a simple programming cable, and it's really only included in the slides as a reference. That's one way to do it, but there are also many other ways. On one side, on the left side, there are the pins on the microcontroller. AVR means it's simply a microcontroller series from Atmel, and it has, for example, a pin for ground, and the other pins are numbered, and you connect them to pins on the parallel port. So you get a simple parallel port plug, connect it through, and then add resistors. You don't have to, but they don't really add much. It's a relatively messy solution, though electrically the thing is quite questionable, which means it can happen that if the circuit is not okay and the Atmel is not really running and some obscure things happen, it could somehow damage the parallel port or do even more. So it's not recommended, but it works. The advantage of the thing, of course, is that it's super simple and you can solder it yourself for a few euros and program things with it. I still use them, but only in circuits where I know they work and with an old notebook. So it's not a big deal if something happens. The alternative is, of course, you can always buy a professional cable. That ranges, as mentioned, from 20 to 200 euros. There should be something for everyone if you want that. The alternative is simply to take a microcontroller, program it once, for example, with the somewhat unsightly cable just mentioned, and install another program, not just the firmware that will later run on it, but also another program, which under certain conditions, for me, at Nordlicht, for example, it's a jumper that must be set. When it's closed, the normal firmware isn't started, but rather another one, a bootloader. And this bootloader resides in a specific memory area and is capable of programming the entire remaining memory. So this Atmel reprograms itself. It's quite a complex thing. But the nice thing is, you can write these bootloaders yourself. It's not so demanding, and you can then do the programming, that is, feeding it with new firmware if you wanted to reprogram it over various interfaces. For example, maybe you've seen in the blinking area, there's a nice LED cube where you can play 3D Pong. And this thing, for example, has a connection for CAN bus. It's a bus primarily used in industry, for example in cars, and it's quite resistant to interference and so on. And they wrote a bootloader and are able to program this CPU. So it starts its bootloader, and they send the signals and push the new firmware in via this CAN bus, and I can basically expand this further. There's also, for example, a small robot with an Atmega 8 inside. You program it via an infrared port. So you can come up with various things and are not reliant on Atmel's interface once you have initially programmed it. The disadvantage is, of course, quite clear. The thing takes up space. This bootloader has to go somewhere. For me, currently, it's a free variant written in C, and it occupies 2 kilobytes of the 8 kilobytes the thing has. That's relatively a lot. But my firmware isn't yet so big that it concerns me, and I will eventually write one myself. And the one I'm using, well, when writing the EEPROM, it forgot a left shift, and while reading, it had one too many or something. We'd need to fix something before it even starts. But you can use it. Of course, you have a chicken and egg problem. That's clear, because first, to program this controller via a bootloader, I have to program the bootloader, hence the advice that there are simple cables, and if you're sure the circuit you've placed the microcontroller in works, then it works too. You can use it, so it's acceptable to use it. If not, you buy a professional cable from Atmel itself for 200 euros and be happy with it. So, okay, what does a CPU actually look like inside? The Atmega 8, that's a chip with pins on it, whether as SMD or not. You have to consider how good you are at soldering. So what does it actually include? And the really important thing is different types of memory, because without memory, such a processor could do relatively little. We have flash, that's memory. So it's a flash ROM, which I can write to, and then it's static. We have 8 kilobytes of that. The main program is in there. That's where the CPU starts looking for its instructions, and commands are read from there. Oh dear. Okay, well, we'll just ignore that. macOS is great. We have 8 kilobytes of flash for instructions, and that doesn't sound like much in the era of gigabyte hard drives. But when you consider, I wrote a firmware for the Nordlicht that creates great colors, communicates, is intelligent, decodes infrared, and has many example scripts and debug routines. And the thing is currently large, 4.3 kilobytes in total. And that puts it into perspective again. So you might think it's little, but it's actually quite a lot when you have to fill it. The thing has RAM, like any other computer you might know. That's 1 kilobyte. Sounds pretty little too. The Nordlight stuff, as you can see in the blinking area, uses only about 200 bytes of this 1 kilobyte RAM. Although there are still a few debug routines buzzing around in it. Then there's a third type of memory, which is RAM. You can't even program it. It is simply used during operation to store things like variable values or structures. Or I have, for example, for the color value that the node light is supposed to take on, it can take on different colors. If you're interested, check it out. It's in the blinking area. I've stored the color for the target brightness value of each color in RAM, for example, because it changes all the time during operation and it's not a static value. So it doesn't make sense to program it statically into Flash as it just changes all the time. That's what the RAM is for. Then there's a third type of memory, namely the EEPROM. If a computer has BIOS, you might have heard or seen this before, the EEPROM stores its data. You can store data there. For example, you can store configurations there. It's planned soon for the node light. I bring this up as an example again because it's my very first microcontroller project. And you can store configurations in there. For example, I plan that you can use an infrared remote control, which already works, to tell the node light to execute a specific script, i.e. a specific color sequence, and then save it in the EEPROM so that when I turn it on next time, I get exactly this script and not some other one that it just remembered. And the EEPROM is a mix between Flash and RAM, you could say, because on one hand, I can program it very easily from the microcontroller, and on the other hand, it's very easy to read and quite dynamic. So you can also store other things there. You can, of course, also misuse it. I might even do that, I thought. If the space in Flash isn't enough, then I thought I might just also do color sequences in the EEPROM to be able to store them, simply to have space. But 512 bytes aren't much either. You could maybe add something extra, but that's not so important. These are now the three basic types of memory a processor has. So the other important thing is registers. Registers are something quite obscure. If you started directly with high-level languages like I did, it's a bit hard to understand. On one hand, you have memory, and on the other hand, you have the processor. But how do they actually communicate? And those are registers. It's always the way at a very low level in the CPU. A memory unit is loaded into a register, and there it can be processed by the processor. The result is pushed back into a register and then transferred from this register back to memory. That means everything essentially runs through the registers and values are always loaded into them, processed, and pushed out again. That's actually what you do all the time when programming in assembly. There are different registers. On one hand, there are the regular working registers. So if I want to add two numbers, I use the registers. In the Atmel AVR 8, these are R0 to R31. So I have 32 of them. By the way, in Intel CPUs, there are significantly fewer. That's one of the reasons why Intel isn't so great. But that's another story. There are special registers, for example, when I make comparisons between two values, which also have to originate in registers, I have to remember the result somehow. So if I test two numbers to see which is greater, or if the first is greater than the second, then the result has to be stored somewhere, because otherwise I can't do anything with it. And if the first number is greater than the second, then the result is written into the status register. Another very important thing is the PC register, which stands for program counter and is simply a pointer. It contains an address, specifically the address of the currently executed instruction. We'll see this in examples shortly. The third important type of register is the configuration register. The Atmel has an awful lot of hardware integrated. It's incredible what fits in there. And these are counting registers. These are autonomous counters that do something. These are communication interfaces, such as the serial interface that's included. There's IC included. There are all the pins that I have laid out as wires, which I can configure as inputs or outputs. And what the pin is set to at any given moment, I can, of course, change at any time. What this pin is supposed to do right now, I set by configuring it. And I do that by writing a value into a special register. For example, in the AVR 8, there's a port, that's what it's called. These are 8 pins that are let out. They're called PB0 to PB7, and I can configure them. They can be inputs or outputs, and what they currently are, I set by writing values into the DRB register. These acronyms are terrible. It's unbelievable. So I don't know how they came up with this stuff, but the awful thing is that if you do it for a while, you start coming up with such acronyms yourself. It's really dreadful. And DDRB stands for Data Direction Register, which is actually logical, but nobody can remember. And DDRB means it's the Data Direction Register for port B, i.e. for these PB0 to PB7. And what I write into it now, so if I have this register, it's an 8-bit CPU, which means each register contains a byte and exactly 8 bits. That means I have 1 bit per pin coming out there. And if I write a 1 in there, I'm telling the CPU, yes, make this pin an output pin now. That means I can apply 5 volts there, or I can apply 0 volts there. So I can apply logical 0 and 1 there. If I write a 0 there, I'm telling the CPU, yes, make it an input now. Then I can read from it, and it samples it already, and I can directly read the value from another register that is currently applied to this pin. So these acronyms are really awful. It's really dreadful. Exactly, that's again about the working register. Each register contains exactly 1 byte, which is 8 bits. This is an 8-bit CPU. In contrast, a 32-bit CPU has registers that are 32 bits long. The registers are just 32 bits long there. There are 16 low registers and 16 high registers. So these are the 32 working registers we had earlier, and they are divided again, and there are 3 of them that can be combined as a 16-bit value. You actually encounter a problem with, for example, the program counter. There's 8 kilobytes of flash, and the program counter is the pointer that points to these 8 kilobytes, somewhere where the current instruction is. The problem is, if it's only 8 bits, then it has exactly 256 different states from 0 to 255. I could therefore address a maximum of 250 bytes. But that's not enough. I have 8 kilobytes, which is a bit more. They thought, okay, we'll make it about 12 bits, add something to it, and write it in 2 different registers, and treat them as if it's one large one. The exact same applies to the stack pointer, for example. We'll get to that later, what exactly it is. This is also a pointer to a memory area, in this case in the RAM, where the stack begins. We'll get to what that is shortly. And there are 3 sets of 2, which are the registers R26 to R31. They can also be used in paired mode. If I want to read something from the RAM from my program, I can use a pointer register like this. Because, of course, the RAM, as we had earlier, is exactly 1 kilobyte in size. That's also significantly more than the 250 bytes I could address if I only took a single register. So we also take 2 there. It's always a bit tricky. You have to double all commands and make sure that it's still synchronized between the registers. But that's another story. So then there are these special registers that we already had. The most important of these is, of course, the status register. It contains, for example, the last comparison operations when I compare 2 numbers, whether they're greater, smaller, or so. It contains the result of the last comparison operation. Also important is the program counter. We had that earlier. That's the location in the flash where the current program is executed. And what is also important is the stack pointer. It points to the location where the stack is. What that is, we'll see shortly. So we had 3 types of memory: flash, RAM, and EEPROM. We had working registers R0 to R31, and we had some special registers. So the thing has several hundred registers, and the datasheet for the whole story is well over 300 pages thick. I haven't read it completely either, and if you ever decide to tackle it, please do yourself a favor and read it in very small pieces. It's incredibly dry to read. Okay, now let's have an example of the command syntax, because somehow we've talked a lot about what's actually in the CPU, but we don't yet know what the commands look like. And for example, these are very simple commands. Let it sink in for a minute. You can see there are 4 lines. They start with a command, then a space, and then 1 or 2 parameters. Oh, something is missing there. Okay, at this point, there's still a comma missing 16. That's a bit inconvenient now, but just imagine there's a comma R16. The command consists of a command at the front, usually 3 or 4 characters. That's a so-called opcode. It's an instruction that the CPU can execute directly, so it's embedded in the hardware. If it says LDI, it is translated into a number by the compiler. And if that number for LDI is there, then execute this command, and then come 2 parameters. It can also be 1, depending on the instruction. And in this case, LDI means load immediate, which means load into the register indicated as the first parameter, the value that follows. This means load into register R16, the value 255, and 255 is simply 8 ones in a row. So now that's stored in register R16. So if I now want to configure my pins PB0 to PB7, which we had earlier as output registers, as output pins, we need to write ones into the DDRB register, the data direction register for port B. We do this with the command that is written below, out DDRB16, which unfortunately isn't written there now, but I will add it shortly. Then this tells the CPU, please copy this value that is in register R16 into the other special register, and the bit juggling between the different registers essentially constitutes the entire programming. You do this all the time. It may look a bit stupid, and when using C, ideally, you don't see much of this. But the C compiler does nothing else than translating it into such commands and shuffling with registers. The next line is again the LDI that we already know. So LDI loads a value into a register. In this case, it loads the value 0 into register R16, and then another register is used, namely port B. We haven't had that yet. If I have configured the pins PB0 to PB7 as outputs, I can write into the port register what should be applied to these pins, whether 0 volts or 5 volts should come out. If I write a 1 there, 5 volts come out at the pin. If I write a 0 there, then 0 volts come out, and in this case, I write a 0 there. You can see it here now. I load the 0 into register R16 and copy the value from register R16 into the port register. So all pins PB0 to PB7 are set to 0. If you have any questions, please feel free to ask, raise your hand, then I'll address it, and you'll get a microphone. Okay? Yes, sure. Wait a moment. Wait until you have a microphone.
In the second line, isn't the out DDRB just for switching, to switch the port as output?
Yes, exactly, you can.
You wanted to write in there to copy it?
Yes, well,
Not another line in there where it's copied up? Like the last line out port B?
yes, of course, I lost the comma R16.
But shouldn't there be another line, right?
Once again, please.
But shouldn't there be another line, right?
No. So just imagine the last line is also at the second line. That's exactly the same. This causes the content of register R16 to be copied to DDRB.
Yes, but it must be switched first so that it is considered an output, right? Which is written in the second line.
Pardon? Yes, I think that's correct too. I copied this from an example that worked because with the first 2 lines, I configure all PB pins as outputs, and in the second, third, and fourth lines, I set these outputs to 0. That's what's happening there. Okay, so any more questions? Back there, up front as well.
Can you set individual pins now, or do you always have to set the entire port B or port A or something?
You mean whether you can turn individual pins on or off regardless of the status of the others?
No, not that, but whether I can say PB1 is an input and PB2 is an output, or...
Yes, that's possible. You can do that at any time. You have a total of 8 pins, PB0 to PB7, and for each of these pins, there is a separate bit reserved in the DDRB register, and you can set each of these bits individually. If you set only the first bit to 1 and the rest to 0, then you would have PB0 as output and the rest as input. That's not a problem.
Okay, all right, thank you.
Another question up front.
So really simple question, actually. How does it look? You said it can also be programmed with C. And how compatible is this assembler code now with X680 assembler? Or so how portable is it from Atmega 8 to 1632? So that's also an important question, because if I write such source code and it's totally proprietary, in 5 years it's different. How does that look?
Well, first of all, every processor, meaning every Intel processor and every Atmel processor, has its own assembler syntax. That means these commands, as they are, only exist on Atmel, only in this Atmega series. There are other series from Atmel that have completely different commands, and the commands for an x86 Intel processor look completely different again. So that means there is no compatibility between different architectures like PowerPC, Intel, Atmel. They are completely different. That's the reason why high-level languages were introduced back then, to write a thing once. And then I have a C compiler for the respective architecture, and it translates that into the corresponding assembler commands for this CPU. So the compatibility between the individual megas, for example, from Mega 8 to Mega 16, usually not much changes. You can do that directly with some small adjustments. Most of the time, the biggest difference between Mega 8 and Mega 16 is really only that the Mega 16 has a bit more memory. That's basically all right. Any other questions? Otherwise, let's continue for now. So later on, we can ask questions again, and you can also discuss with me afterwards. That's absolutely no problem. We've scheduled time for that afterwards. So, okay, now these are the 4 instructions we just had. That's not the only thing. I also want to write a program at some point, and it can't be that this program consists only of 4 instructions. That would be a bit boring. The problem you also have on a microcontroller is that you don't have a running operating system. So if you want to write a program that runs on it, you have to do everything yourself and for each individual program. That means, for example, we have to initialize all the hardware every time. If I have two different programs that use an output pin, then I have to execute the same thing in both programs. I have to configure this output pin in both programs, which means I have to write my own operating system, and I have to do all the initialization in each individual program. There's no way around it. So, for example, this is a prologue for a program. First, this instruction with a dot in front means they are processed by the compiler. The processor doesn't get them. So that I can use these funny acronyms at all, because actually they are just registers located somewhere. And where exactly they are, I don't need to know precisely as a programmer, because it's in a configuration file, in this case called 8f-inc. So it indicates that the DDR-B register is located there, and that's where you have to get from. The compiler translates everything into numbers, but you can't program so well with numbers. So symbolic constants have been introduced, and they are found in this M8f-inc. The next command is also relatively important, .org directive. This means that all the commands I write into such a file and later burn onto this microcontroller are basically all stored in the flash. First of all, because the program is stored in the flash, it's simple. The instructions are there, and that's where the processor retrieves them. So at the beginning of the flash, there's a special place called the interrupt table. There are commands there that are executed during certain events. At the very first position, there's the command that gets executed when the processor is turned on. And to make sure I really write the next line at the first position, there's this command.org. It sets the current position in the flash. That means .org 0 simply means please set my next instruction right at the beginning at position 0. That's the instruction that gets executed when the microcontroller is turned on. In this case, it goes with its pointer right to the beginning and writes the instruction, please jump to the location reset at the beginning. We will define them later. That doesn't fit on one slide. This is just the beginning for now. After that, several other commands will follow. So there can also be others that would be executed during certain other events. For example, I can configure it so that if I have a switch on a special pin and press or release this switch, I can have certain commands executed, and I would write them behind it. This area is also variable in length. That's also a difference, for example, between Mega 8 and Mega 16. With the 16, it should definitely be longer, so that I don't specify a constant position now. There's a constant for that again. It's called int vector size. That's the number of special commands that can be inserted at the beginning. And I don't want, when I start slapping my program behind it, that if I configure something wrong and somehow randomly hit this one pin, any wild commands are executed. That's why I simply write the following program after this section with the special commands. And that's exactly what this org infector size does. So it tells him the next commands, please, a little later. And precisely the piece that these special commands are at the beginning. So after that, the program continues. I copied the top line again up there. So that's now behind it. There are 111 labels. That's always a string followed by a colon. So that's a point that I will reference again at some point. And I already did that in the previous slide. There I tell it, at position 0, please. As soon as the processor is turned on, jump to the position, reset. I don't need to remember exactly where it is now. The compiler does that for me. It simply replaces it with a number, namely the address where this reset is located up here. So when this program is burned onto the microcontroller and turned on, the following happens. It jumps. First of all, it jumps to the position, reset. That's a bit exactly the first instruction after this special area with the special commands. And the very first thing it does again is, we just had that, it loads, oh, there's something missing. The comma is missing again. 16, it loads 255 into register R6 and configures all pins PB0 to PB7 as outputs. After that, it loads a 0 into register R16 and writes it into the output register. So that means all pins are at 0 volts. A question. I had a question about this loop routine. It says in R17 port B, but the input port is pin B, not port B. So if we were actually reading in now, that's correct. We will get to that immediately. Let me just explain. Now we have, so that's a justified question, and I'll address it immediately. But we'll do it simply from top to bottom. So we configure, as we saw earlier, these 4 lines, configuring PB0 to PB7 as outputs and setting all to 0. So, and then it's the command from above again. I load the value 255 into register R16, a series of 8 ones if you look at it in binary. So then I have another label, which is called loop in this case. That's what your question is about now. And the first thing I do, that's a command I haven't had yet. The admin has about 60 or 70 commands. There's also a reference PDF where you can check how they work. And this command does nothing else but copy the value from a special register, in this case port B, back into a normal working register. That means, in this case, executed for the very first time, there will now be the value 0 in R17 because I wrote the value 0 into port B earlier, and I copy this value that's currently in there back into register R17. That's not particularly efficient the first time, but it will soon become clear what happens with it. So the next command is I now have 250 in R16 and 0 in R17. The next command is EOR, which means exclusive, or that's a mathematical function. And in this case, when I say exclusive of R17, R16, so 0, R0, 250, and the following simply happens. Every bit in R17 is inverted. If there was a 0 before, it is then a 1 afterwards and vice versa, and then I output these inverted bits that I simply swapped. So I read the bits as they are, invert them, and write them back out. And then I jump back to the position loop and do the whole thing again. Now it makes sense because I know I didn't remember what my output status was before. I simply read it back from the output register. Does that answer your question?
No.
Not really? Okay, then please the microphone again.
In total, there are 3 status registers related to port B, namely DDRB. There is the data direction register, whether it is defined as input or output. Then there is port B, which is the output register. You write there what should be output when the pin is defined as output. And then there is the input register, which is pin B. That means all the values are there. So if I have configured a pin as input, then the values where I have my input are accordingly 1 or 0. That's why I don't understand, because when reading, we should correspondingly push the value from pin B into R17 and not from port B.
That's correct. So he said, I should actually, if I have configured these pins as inputs, then I can read the status at that pin, whether the button is pressed or not, from the register pin B. That's correct so far. Yes, but I don't have any input pins. I haven't defined an additional register, but I simply read back the status I previously set for the output registers. This is not the input at these pins, but what I previously pushed out as output. If not, we can talk about it again later. Okay, are there any other questions about this? Otherwise, let's move on to what this actually does in hardware. If not defined otherwise, an Atmega 8 initially runs with an internal clock. This clock is about 1 megahertz. And if I now attach an LED, for example, to one of these pins PB0, like a lamp, and run this program on this whole setup, then the following simply happens. I see this LED with slightly dimmed brightness. This is because every instruction, well, each instruction takes exactly 10 to the power of minus 6 seconds to execute, since most instructions require 1 cycle, and a cycle at 1 megahertz is about 1 times 10 to the power of minus 6. That's a pretty small number. That means I need 1 instruction. So when I enter the loop, I need 1 instruction to read it, 1 to invert it, and 1 to push it out. Then I need 2 instructions. That's the jump. It requires 2. Then I need 2 instructions to jump back up and read it again, invert it, output it. And so my LED is on for about 3 cycles and then off for 3 cycles again. That's not quite what I wanted, because originally this program was meant to make an LED blink. The problem is I can't see it blinking because the whole thing is happening too fast. So now this is an example of trying something and not having anything good come out of it. But that's one of the problems I had in the beginning. I couldn't manage to wait. I tried to simply make the LED blink, and the problem is the processor is too fast for me. Well, that's it for now. We see the complete example here again. It's just the whole program briefly copied together. We just had this prologue above. which might be a bit hard to read. I've done it separately now. This is the whole program. Above is the prologue, and below is this small loop. So, okay, one of the very important things if you want to do more serious stuff with all this, I want to call subroutines at some point. I want to be able to say jump to another place, do something, and then jump back to where you were before. For that, I need to remember something. Specifically, I need to remember the current program counter, i.e. the place where commands are currently being executed. Then I have to jump somewhere and then return to the place again. I need to remember all of that. And since this can happen multiple times, like I can jump into a subroutine that jumps into another subroutine, and again into another subroutine, and again into another subroutine, then I have to remember a position 4 times over, and then I do that with a so-called stack. It's a stack memory. It's a data structure that is relatively simple. I just always put something on top and can only take it off from the top again. It's like having a storage room. You can put things in there, but you can't access the things at the back directly. You have to clear out the front first. On a CPU, that's how it's done. I have a certain memory area, my working memory, my RAM, and I set the stack pointer. So far, I haven't needed it any other way. If there's something else at the back, you can do it differently. You set the stack pointer at the end of this memory, and it grows backwards. I write my first program counter, which I need to secure, right at the end of the memory, and then set this stack pointer down 1, meaning it points to the second last position. And I initialize the whole thing by loading 2 things. As we just saw, the stack pointer is 16-bit, so there are 2 8-bit registers, SPL for the lower register, and SPH for the higher register. And we have a constant ramend, which is defined in the include file I had earlier. That's also the case with Atmega 8, Atmega 16. That's different. But I don't care about that. I simply load the other configuration file for the other processor and still have my constant, the way I want it. And these low and high are directives that the compiler processes. So it already extracts the upper and lower byte for me, so I don't have to worry about it. And so I load the lower byte of this constant ramend into register R16 and then output it to the register SPL. I do the same with SPH, and then I'm done. Then I've initialized the stack pointer so that it points to the end of the working memory. So, exactly. That's what I just explained. For subroutine calls, I obviously have to remember where I was, so I can return there. And simply using a register for that won't be enough, because I can do it multiple times. I can have subroutine within subroutine within subroutine, and then I need to return 3 times, and for that, I use the stack. The command to call subroutines is called orcall. It does it completely automatically. So the position is saved. And then when the subroutine returns with the command return, or ret, the program counter is reloaded and execution resumes at the place where it was before. So this is an example, for instance. I've got that again. I've omitted the prologue. It would be too big. I have a reset procedure that runs when the processor is turned on. I initialize my stack pointer and then do an rcall test. Rcall means telling the processor that this instruction also takes several cycles. That's a somewhat longer story. Tell the processor, please save the current execution position, so there's nothing in between now. That's relatively boring. Normally, quite a bit can happen in between. Save the current position where I am on the stack, and then jump to the location test. Something can happen there. These points now represent that, and then please return, and he jumps first. From the rcall, he jumps to the test. Then it does something as appropriate as possible, and afterwards, the return tells it, jump back to the position. So, and that's actually quite a complicated matter, until you get it right. So for me, it took about 2 months of work from scratch to being able to call subroutines. It may not be especially fast, but it's really tough if you don't know anything to begin with. Exactly. That's the big question of the event. What the heck is an interrupt? Now, we've done quite a lot in terms of theoretical preparation, and normally on regular PCs. I learned about it under DOS when I had a sound card in my computer back then, and I had no idea, and it needed an interrupt. But what is that actually? Unfortunately, hardly anyone knows that anymore. And with microcontrollers, you can explain this very well, because we just had subroutine calls with the program counter that is saved, and it jumps to another place, and then it comes back, and then interrupt is simple. People thought about it and said, things like counting. The CPU doesn't have to do that all the time. We can just build it into a hardware circuit. And simply when a specific counter state is reached, we can say, okay, now it's reached, and now something happens. That was also at the beginning of this special area I talked about, where you write instructions that are executed at certain events. That's exactly it. I can configure a counter. The Atmega A8 alone has 3 of them, so that a certain instruction is executed at a specific counter state, which stands at the beginning of the flash. At the beginning of this memory where I said earlier, there are special instructions in it, and that is precisely what an interrupt is. This means it halts the current execution of the code. Wherever it is, it halts, jumps to the beginning, finds the appropriate spot for this event, and then executes this instruction, having previously noted where it was before, does something like resetting the counter, then jumps back. And that's an interrupt. Exactly, that's the example timer. Exactly now, I hope I've told you a bit about Atmel CPUs. How am I doing on time? 10 minutes left. Okay, then I would say I'd actually hope to get a somewhat smaller room so that one could demonstrate. I fear, however, that it won't be very useful if I set up a chord light here and show it to you, because you won't see anything after the 3rd row. I hope it's become a bit clear what a microcontroller is and what it does. It was very, very compact. If you're interested, dive into it. I'll add a slide with important URLs, for example, microcontroller.net, which is a very nice tutorial for this. If you're interested, read up on it, but be aware that once you've started, you really won't be able to stop if you have some interest in it. Yes, okay. First questions. Any more right now? Yes. You said that one of the problems is that you need both a functioning sync circuit and a functioning program, and then also have to determine if it is correctly loaded. There is.
Isn't there a smaller part of it, like a simulator that just runs on the computer, so you don't immediately need a circuit and the properly loaded program allowing you to try one thing at a time?
Yes, there is. For one, the original software from Atmel. The thing is called AVR Studio. You can download it and simulate all Atmel CPUs with it. Unfortunately, it is a proprietary solution and is only for Windows. For Linux and all other operating systems, there is Java software. Either it's called Simula VR, I believe. That is a Java software. It is a general simulator for Atmel architectures. Unfortunately, they don't have the Atmega 8 included yet, so I unfortunately couldn't use it for that either. I did it this way for my application. I wrote the code this way, debugged as best I could. Partly just with serial outputs that come at specific points, but that creates a timing problem if it goes very fast, faster than I can send serially. And I'm also debugged some timing issues with the Windows software because it unfortunately doesn't work any other way yet. When Atmel AVR is able to simulate it properly, it will become much more interesting. Unfortunately, that's the only thing that bothers me about development under free operating systems. Unfortunately, there's no good simulator yet, and you can work with circuits. The Atmega 8 doesn't have it yet. The Atmega 16 and others have an interface called Debug Wire. With that, you can use AVR Studio together with a very expensive device from Atmel, or you build the Evertool, which is a cheaper replica. And with that, you can do step-by-step execution on the CPU, live in the circuit, and debug all the values, register contents, everything in AVR Studio. That's actually a very nice thing, unfortunately proprietary.
How many cycles does such an interrupt roughly cost? And above all, what does the return from the interrupt cost again?
The interrupt costs relatively many cycles. I tried it out and took a look at what happens with the simulator. That's about 8 clock cycles it needs. It has to, for one thing, push 2 bytes onto the stack. That takes quite a while because it has to write that on. It has to adjust the stack pointer so it points to a free space again. Then it needs to jump forward to the place where the event for this interrupt is located. And then it has to jump somewhere else again because I only have the opportunity for a single instruction up front. And that costs relatively many cycles, about 8.
And so nothing of that kind is done to somehow protect the register contents? That means I always lose additional time by having to manually process it further in the stack?
Exactly. All registers that I use in a subroutine, especially in an interrupt routine, like the status register, I have to manually save. That's the disadvantage when writing directly in assembler. I have to take care of it myself. And if I write in a high-level language like C, there is GCC for Atmel CPUs. If I write for that, it takes care of it. The problem is, it does a lot. So it first saves, first secures all registers. That means I jump into my interrupt procedure, and then GCC, the code it produces, first secures all 30 registers. That's also such a thing again. With timing critical matters, one would have to resort to inline assembler in C anyway. Any more questions? Okay, then I hope you enjoyed it and that it generally gave a bit of an overview of how such a thing works, how you actually do it. There are very good tutorials, including those that directly suggest hardware circuits that you can solder on, which work. I hope it helped you a bit. Thank you.